Howdy, everyone. Happy Monday. I hope you had a nice weekend and I hope you're doing well. On this day, April 12th in 1945, Franklin Delano Roosevelt died from stroke. He was the only president that had ever been elected to 4 terms, and he was just starting his 4th term. I have one student saying that he wishes he were doing well. Well, I hope you're all doing well. Harry Truman became president in 1945, and he had a very troubled presidency. During his reign, all of Eastern Europe turned communist, and the United States could have done something to prevent that, but Harry chose not to. I don't often like to say things about politics, but it was a sad period for much of the world as we had the Soviet bloc created for more than 50 years after that. The Korean War also started under Truman, and when Truman's reign ended, he could have run for president again in 1952, but his popularity at some point hit as low as 23%. Revisionist historians sometimes like to raise his stature, but many of us feel it was really a terrible presidency. But enough about politics, shouldn't have gotten into that. I'm showing you the 17 equations that changed the world. I'm not sure I would have written these all the same way or picked the same equations. You'll notice we have the time-dependent Schrodinger equation version here. Our statement of second law of thermodynamics is made kind of simplistic. We are talking about an entropy, and we do want it to get larger. And we'll talk more about that today. Relativity is really not E equals mc squared, so I have my skepticism about who put these slides together. This is conversion of mass into energy. Okay, just as a reminder, you'll remember we went through and we looked to see what the relative populations of quantum states would be. We came up that some quantum state n sub I, basically its fraction of molecules compared to all the number of molecules could be given by this. We remember that beta is 1 over kT, so each population is proportional to e to the minus e sub I over kT. The denominator here we defined as the partition function, and we've now been seeing that there's lots of things we can do once we have a formula for the partition function. One of the first things we came up with, and this is a formula that you'll be expected to apply on your 3rd exam, which, by the way, is a week from Wednesday. If you look at your schedule, it says we're going to have a review for the exam this Friday. What I'm actually going to do is continue with lectures, and in the lectures we have something called the super problem. And this is essentially a practice problem applying statistical mechanics. So that'll be part of our review. And we will continue next Monday also to review for the exam. Again, that'll be next Wednesday, a week from Wednesday. Okay, so here then is the formula that one would use if you want to calculate internal energy, which you would often call U minus U naught. You need to know Q, and you need to be able to take the derivative of Q and see what you get. And we saw also that Q gets to be large when you have many quantum states populated. It's small when there are not many populated. But it is not an exact statement of anything. It's just a useful number from which we can calculate things like internal energy and entropy. Okay, so our idea with the whole derivation was that we needed to maximize the W, the weight of a distribution, And initially, I sort of lied to you a little bit and said we just want to get the one most probable W that we can for one set of quantum states and get those populations, and that's going to be our most probable situation. But that would have given us a fixed universe with each molecule specifically in some quantum state, and we would not have been allowed to have any entropy. So what I consider to be perhaps the most difficult part of understanding quantum mechanics is this business of having an ensemble surrounded by a reservoir at fixed temperature. And each member of this ensemble has a fixed number of molecules, has a fixed temperature, fixed volume. And instead of coming up with exactly the most probable or coming up with exactly the right energy we're putting in, we're letting the energy fluctuate slightly between all of these different boxes. All of the energies are very close to each other, but there needs to be some fluctuation for us to have entropy. Anyway, the result that we came up with then was we would come up with a canonical partition function, which is equal to the molecular partition function, little q, and it came out to be q to the nth over n factorial. And I keep telling you this, but just think about the magnitudes that you have. If we have translational levels, q's are going to be maybe 10 to the 30th. If n, capital N, is Avogadro's number, that's 10 to the 23rd. So we have 10 to the 30th to the 10 to the 23rd divided by 10 to the 23rd factorial. So just humongous numbers that we deal with. All right, well, why we wanted capital Q is this will lead us to entropy. We first wrote down Boltzmann's famous formula, famous enough to have made it onto a Nicaraguan stamp. I stated it for you, and then I quickly went through some mathematical statements to show you where it came from. And I think where we stopped last time was I was going to do the same thing with this formula here. So if we write the Boltzmann formula for entropy, S is equal to K log W, W is really not a meaningful thing for us. We have to convert it into, well, at least the Q's so we can get something out of them and figure out actually what the entropy is. All right, so again, here's a bunch of math we don't have time to go through. It's stuff that all of you would be able to do. And when we get done with it, the formula we come up with in this box here, and this again is something we will use, for example, on your third hour exam, it's a way to calculate entropy. So we've seen that we can calculate capital E, which is also U minus U naught, the internal energy above the 0 point. We have a formula for calculating that. So we divide that by absolute temperature. That's the first term. And then the second term comes from K natural log of the canonical partition function. I told you last time that all of our systems are going to be indistinguishable particles. So probably in the future, I might want to just leave out all this stuff about distinguishable particles. The main reason I think books include it is this is the one that comes out more readily from statistical analysis. When you go to indistinguishable molecules, we have to stick this capital N factorial into the denominator. Okay, bottom line is realize you can do the math. You won't be expected to derive it, but appreciate the formula that we come up with. This is the formula for entropy. And then for capital Q, this is Q to the N over N factorial. So when you put that into this equation, this is the result that you get. But what you see is you will have a capital NK in front of this term. And I pointed out to you last time, the number of molecules times the Boltzmann constant is equal to the number of moles times the ideal gas constant. So K, for 1 mole, Avogadro's number of times K is equal to the ideal gas constant. Later today, we will start applying statistical mechanics, and then I think a lot of this will start making at least some more sense for you, seeing what kind of values you can get quantitatively from these calculations. Anyway, so this is a useful formula that you can use for calculating entropies. In fact, if you do it this way, you don't really have to resort to calculating what capital Q is. If you do calculate capital Q, then make sure you use this formula for calculating it in terms of the little q that we have here. Okay, so let's start talking about applications. This, again, is not chapter 15. I'm sorry that it's not been updated, but I think your book has sections on the background for statistical mechanics that we've gone through, and then it starts applying these. So the bottom line is we're always going to have to know what the molecular partition function is. Our definition for it is that we sum over all possible quantum states and add it together. Eventually, the series dies out. When you get to very, very high quantum state, like 10,000 wave numbers above the ground state, then the e to the minus e sub I term basically becomes 0. So it self-truncates when you get into high enough levels. As I've been telling you, the quantum states we now consider are all of them: translational levels, rotationals, vibrationals, and possibly electronic. But you'll see most of the time we can ignore the electronic states. Okay, so any quantum state that we look at, so any molecule that we're looking at is going to have a certain total energy, and it'll be the sum of all of these individual components. Mathematically, if we plug this up into what Q is up here, you see all of this turns up to be in the exponential. If we have sums in the exponential, we can then write it as products. In other words, if we take Q for translation as a summation of the translational levels, that would take care of the first term. Then our second term would be Q for rotational levels. That would come out of this expression. Then we would have Q for vibrational ones, and then Q for electronic ones. So what we have to do is we have to figure out what a Q is for each of these. Now, luckily, we've already done it for translations. Luckily, we're going to find that QE for electronic states is typically 1, so we don't have to do anything there. So our biggest challenge is having to figure out what the rotational partition function is and what the vibrational partition function is. So a reminder, we did this for translational levels. The way I like to present it was we came up with a translational partition function is tau times volume, and tau was equal to this. Whenever we have our third exam, or whenever computers do these calculations, or if you do problems in your book, I recommend just using this expression right here. You can break tau into what the mass is in atomic units, temperature in degrees Kelvin. If you multiply it by 1.88 times 10 to the 20th, and then multiply by the volume, you'll have the translational partition function. As I showed you in an example before, I think we had H2 gas at 25 degrees centigrade. We had a very, very large number. The numbers can be the magnitude of 10 to the 30th. If you go to your book and some others, but not all of them, like to define the translational partition function like this: volume over lambda cubed. So what you can see is 1 over lambda cubed is basically the same thing as my tau. And why the book thinks this is easier to work with, I don't know. Here's the expression for capital lambda. You'll see we have the 2 pi mkt to the 1/2 in the denominator. I have it to the 3/2 in the denominator because there's a cube here. So don't be bothered by the fact that this is what your book is going to be giving for you. Okay, so translational level calculation should be very straightforward for you. You use this formula right here, which will be on the cover page of your exam. You just have to put in the mass in atomic units. So if you were doing carbon dioxide, you would put in 44 for the molecular weight of carbon dioxide, for example. And then temperature to the 3/2. Some students in the past have get confused on the calculators, taking things to the 3/2 power. Basically, what I do is I take the square root of t, for example, and then I multiply it by t itself, and that's t to the 3/2. But depending on whether you have a Hewlett-Packard or Texas Instruments calculator, and you do y to the x power, sometimes it's easy to get the y and the x confused when you do that. So if you like it, use my method of getting the 3/2 power. Okay, rotational levels, all partition function basically are defined as the summation of all the levels. And so in our examples for rotations and vibrations, I'll show you how you can do it both ways. So we're going to have an approximation formula, and then we're also going to have a direct summation method. To start with, I'm going to take the simple method for diatomic molecules. So if we want the rotational partition function for a diatomic molecule, which has these energy levels, we use this formula up here for minus E sub j. We have a degeneracy of 2j plus 1 for each rotational level, as we'll learn. And then we sum all of these terms together, starting at j equal to 0. Don't confuse matters, because last time I told you that we wanted the lowest energy level to be E sub 1, but basically j equals 0 is the E sub 1 level for statistical mechanics purposes. We have to start from the lowest level. Statisticians don't like to start from 0. They like to start from 1, and that's where those definitions come from. Anyway, notice what you have to do for each energy level. You then have to calculate what the energy is. You divide by KT. KT is 207.2 wave numbers at 25 degrees centigrade. You have to multiply it by 2j plus 1, and you go j level by j level. For the very first level, j is 0, so 2j plus 1 is 1. The exponential term, e to the minus 0, is 1, and so the contribution to Q will be 1. You might want to keep this in mind. Anytime you do direct summations, the lowest energy state with energy 0 will always contribute 1. So you can never have a Q value less than 1, whatever you do. Okay, during the summation, we next go to j equal to 1. The degeneracy 2j plus 1 becomes 3. The exponential term becomes, well, first the exponential term becomes 0.90. So we're doing HCl. B is 10.6, so we're going to have 21.2 over 207, or roughly e to the minus 0.1, or about 1/10. And that's where you get the 0.9. But notice then the contribution to Q is 2.71. And this number is also how many times more molecules of HCl are at j equal to 1 than are at j equal to 0. Well, we continue this. The degeneracy goes 3, 5, 7, 9, 11, 21. The exponential term keeps dropping as our energy levels go higher and higher. And already you can see by the time we get to j equal to 10, we're getting very small contributions to Q. So if you take 20 terms, you'll have pretty much the exact value, and you get 19.90 as the rotational uh, partition function for HCl. Uh, when you do take your third exam, I will ask you to demonstrate that you know how to do this summation. I'm obviously not going to ask you to sum up the first 20 terms of HCl, but I might ask you to do the calculation for the first 2 or 3 levels in a summation, so I know that I see how you're doing it. And it all goes back to this equation right here. We'll do some practice problems that will also do this. Now, it turns out there's also lazy man's method, lazy ladies, if you wish, of doing the calculation. And this generally won't give as accurate a result. But if you're having lunch with someone and you're trying to do a back of the envelope calculation, this is generally good enough. And where this approximation comes from is the summation is approximated by an integral. You might remember that the way we got our translational formula, we did the same thing. We had a summation over the translational levels, which were extremely close together. And so the integration worked out very well. Here, the individual quantum states are not as close together. There might be 10, 20, 30, 40 wave numbers apart. And so the integration approximation doesn't work as well. But basically, it says to do the calculation, you take KT in wave numbers. And so the term I'll put in brackets here is KT in wave numbers. At room temperature, 25 degrees centigrade, it's 207.2 wave numbers. And all you have to do is divide by the rotational constant. Also, if you happen to have a homonuclear diatomic molecule like H2 or N2 or O2 or F2 or bromine, Br2, you have to put a 2 in the denominator. And our statistician friends could tell you where that is, but it's kind of related to the Pauli exclusion principle, making sure that you wind up with antisymmetric functions. And if you have a homonuclear diatomic molecules, you're only going to have half as many levels as you might otherwise. If it's not homonuclear, you have a molecule like HF or BRF or carbon monoxide or nitric oxide, you just stick a 1 into the denominator. When you apply this for HCl, you get 19.55. So what are we? We're off roughly 4 parts in 200, so that's about a 2% error. It's not too bad. Most calculations, as I keep telling you, of this type would be done by computers. The computer can quickly add up the first 10 or 20 or 30 rotational levels, get the values exactly, and then you come up with a 19.90. I'm not going to be quizzing you on doing this approximation calculation for polyatomic molecules, but I do want you to be familiar with the formula. In this approximation, notice we have KT in the denominator, and diatomic molecules have 2 rotations. So basically you're getting KT to the 1/2 for each rotation axis that you have in the molecule. A polyatomic molecule that's not linear, it's going to have 3 moments of inertia, and it's going to have 3 rotational constants. And so the approximation formula comes out with a KT to the 1/2 for each moment of inertia. So you get a 3/2 in the numerator, and then you divide by the product of all the rotational constants. And notice there's also a sigma factor, and this is a symmetry number. We don't have time in this course to go into it. Your friendly computer would know what to put in there. But just as an example, if we did ethylene, you might notice there are 4 equivalent hydrogen atoms. Sigma comes out to be 4. It's really related to the Pauli exclusion principle, having 4 appropriate exchanges that you can do to keep your antisymmetric wave function. But that gets rather hairy, so we avoid it. Anyway, the approximation formula works quite easily too. If you don't feel like going to a computer, you know your rotational constants, excuse me, for a molecule, you do the calculation. For ethylene, it comes out to be 661. So the fact that this number is roughly 30 times bigger than for HCl is indicative of the fact that it's a larger molecule. The rotational levels are a lot closer together. A lot more quantum states are going to be occupied, and hence a larger number. Notice the thing I mentioned right at the beginning of the lecture. Our final partition function is the product of all these things. So even though KT is maybe 25 orders of magnitude greater than the rotational value, we cannot ignore the lower values because it's multiplicative. Typically, we're going to find that the vibrational partition functions might only be something like 4.3 or 1.8 single digits. But we still have to keep it in there because 1.5 times 10 to the 30th is still a lot more than just 10 to the 30th. So all of these have to be multiplied together. So these are considerably smaller than translational levels, but still very important. All right, now for vibrational levels, we can talk both about diatomic molecules according to the harmonic oscillator, or we can talk about polyatomics. But basically what you do is, again, you start at your lowest vibrational level, which is defined as having vibrational energy 0. It's actually the 0-point energy. And you sum over all the states that you have. If we're doing a diatomic molecule, you remember all the quantum states look like this. We can't only use the one vibrational frequency we have to consider also all of the excited states. So our energy levels look like this. We define E0 as 0, and so the vibrational levels come out to be V plus H nu. In other words, we ignore the 0 point, we ignore the 1/2 H nu value, and we just start at E1. So if we want to do the partition function for the vibrations of a diatomic molecule with a single vibration, this is what it would look like based on the harmonic oscillator model. I mentioned to you that when we had our thermodynamics research center at A&M, I was often asked about the anharmonicity of these systems too, because if you want more accurate results, you don't want to quite use the simplest formula that you have. Anyway, when you go through all this, and don't worry about the derivation, this is the result that you get. And I'll put this in a big rectangular box because it is an important formula. Right here, this applies to the vibrations of a diatomic molecule with only a single vibration. Many vibrational levels, but only a single vibration. So notice in the denominator, I have nu bar here. I should have probably put a KT over, sorry, I should have put a bar over the KT. So you can see how this comes out to be in wave numbers. So quick calculation for HCl. Our denominator would be 1 minus e to the minus 2886. That's the vibrational frequency. Divide by KT, which is 207. So it's roughly e to the minus 14th. And e to the minus 14th, of course, is 0.000 for many, many, many decimal places. And QV is equal to 1. So all this says is that for a normal system at room temperature, all of the HCl molecules are in the vibrational ground state, and it does not contribute to the overall partition function. I also gave you the example of iodine vapor before. This has a vibrational frequency of 214. So in the denominator, we wind up with the exponential of e to the minus 1.03. You do this calculation and it's 1.58. And when you wind up multiplying this times a number like 10 to the 25th, you see it's very important. So we have to worry about the vibrational levels of I2 if we want to calculate the thermodynamic properties of I2 vapor, for example. Okay, so this was diatomic molecules. And why I put this big box around this formula right here is because it applies, again, to polyatomic molecules, to larger molecules, except that you have to use it over and over and over again for each vibration. So this is the way that it works. You do the calculation for vibration 1, you put in vibrational frequency number 1, then you repeat it for vibrational frequency number 2, and you go through all of the vibrations. Typical molecule will have 3n minus 6 vibrations. So our ethylene with 6 atoms would have 12 vibrations. You would have to multiply this together 6 times to get the overall answer that you have. All right, well, I picked a problem out of your textbook. I think this is still in your textbook. It's no longer 20.5, but let's just do calculations for water for the vibrations. So here are our 3 vibrational frequencies. And here's a hint whenever you work with statistical mechanics. If you're looking at energy levels that are very much greater than kT, then you don't worry about their contribution. So the exponential term for nu1, this first frequency, would be 3657 over 207 at 25 degrees. So that's roughly e to the minus 18th. You don't have to worry about this contributing anything. And the same thing for the third vibrational frequency. This is 18 times greater than kT, so you don't need to worry about it. Anytime your vibrational level is more than about 5 times higher than kT, you just can assume it doesn't have any contribution. All right, well, the middle vibration frequency for water is 1595, so you're going to have roughly e to the minus 8th here for the exponential term, and you could just say, again, that's negligible. If you carry out the calculation to enough decimal places, you'll find that this middle vibration contributes 1.0005. These others contribute 1, and this is your product of those 3 numbers. Now, one reason chemical engineers should love statistical mechanics, or at least the programs that do these calculations, is you sometimes might get involved with a process that takes place at 500 degrees or 1,000 degrees, or maybe even 1,500 degrees Kelvin. And then you would have to know the thermodynamic properties of whatever you're looking at that temperature. And you don't want to have to go into a lab and figure out what the properties are of water at 1,500 degrees. But you can do the calculation. Now, the first thing that you can see, I didn't write down what kT becomes at 1,500 degrees, but it would be about 5 times the 207, so it would be 1,000 wave numbers. So this term would wind up being about e to the minus 3.6. This would be about the exponential to the minus 1.6, and so on. So when you do these calculations, you start getting a little bit of contribution from even these very high frequencies, and then you get a significant amount of contribution from this middle vibration at 1595. So you'd have the term here, this would be e to the minus 1,600 over 1,000 roughly. And so this e to the minus 1.6 results in a significant value here to the contribution. So a lot of this is just grind out stuff, but you need to know what the formulas are. You multiply this all together, and you can see that you have to worry about the vibrational contribution. In physically, what this means is when you have so much energy at this higher temperature, 1500 degrees, the water molecule cannot accommodate all that energy just in its translational levels and rotational levels. A lot of it has to start going into these vibrational levels. And so that's what that number indicates. Down here at 25 degrees basically says almost no energy goes into the vibrational excited states of water, but at 1500 degrees, quite a lot of it does. Now, the one you're going to like the best is the electronic contribution. For our purposes, we can always assume the electronic contribution is 1.0000. This is because electronic levels, with only a few exceptions, are always greater than 15,000 degrees. If you take the exponential term that you're summing, e to the minus 15,000 over 207, that's e to the minus 75th. And I think even your calculators would not show any decimal places that you have out of this. So 1.0 to lots and lots of decimal places. There are a couple of exceptions. There are some unique molecules that have degenerate ground levels. We're not going to get into those. And the nitric oxide molecule, which has an unpaired electron, is quite unique. It's got two angular momentum states that are only 121 wave numbers apart. And so the QE for electronic comes out to be 2.8. But these are well-known exceptions, and the chances of you ever running into any of these are pretty minuscule. Okay, so again, I've gone over a lot of that pretty fast. I think it'll become easier to follow and know what you need to do once we start doing calculations for specific problems. So this is how we go about it. We first have to calculate the overall Q. Again, it's not page 594, but there'll be a table of formulas in your book. The internal energy in terms of capital Q is written by like this. I actually recommend you use the minus n over little q dq d beta, because you always calculate little q first, and it's a lot easier to use that. The entropy, we've just seen today, it's the internal energy over the absolute temperature plus k log q. Ignore the first line here. If our particles were distinguishable, that's what we'd use, but they are almost never distinguishable. We will always have indistinguishable particles. All the molecules will be of the same type. In graduate courses in statistical mechanics, people will look at mixtures, and life can get a lot more complicated. Okay, so as you probably already well know from your Chem E courses, once you know internal energy and entropy, you can calculate all of the other thermodynamic functions. And I have a chat comment. It's not, someone asked, should I have a little q here? I should have written it down for you. This is a correct formula with capital Q. However, I recommend when you're doing okay, I always recommend using this formula. These two are equivalent to each other, but you always have to calculate little q first. So why bother to go over to this formula there? Always do your internal energy calculation from little q. Okay, so we're done with the chat questions, and let's now continue. Okay, so as I said, all other relations come from internal energy and entropy. Now, I think I got through undergraduate education without ever learning what the Helmholtz function was. But your book likes to talk about it, and there's also uh, a useful calculation we can do with it. There's another chat question. Will I send you a summary of exam 3 notes? Yes, I'm going to be sending you a review for exam 3. I'll probably do it tomorrow, that I'll send it out to you. Okay, so Helmholtz function, out of curiosity, somebody sent me a chat message. Have you used this at all in chemical engineering courses? Anyway, okay, quick answers. And the answer is yes. In Thermo 2, you used it. Okay, well, I never used it as a chemistry major. All right, well, turns out if you look at the definition of the Helmholtz equation, it's internal energy minus temperature times entropy. And we have just seen that we can write entropy as U over U naught over T plus K log Q. So now if I multiply through by the T, I've gotten rid of the T in the denominator and I get a T here. So our Helmholtz function can directly be calculated once you know what the natural log of capital Q is. So it's as simple as that. You can immediately get that. So since I never learned about the Helmholtz function as an undergraduate, I never also learned that the pressure could be related to the Helmholtz function. And let's see if we have a new chat question. Someone also wants to practice problems in PDF. So let me write myself a note. Okay. Anyway, so maybe you knew the relationship about pressure and the Helmholtz function. The derivative, partial derivative of the Helmholtz function with respect to volume at constant temperature is definition of the pressure. And so if we put this together using this term right here, we get the KT in front, and then we get the derivative of the log of Q. And the derivative of log, of course, is 1 over Q times the partial derivative of Q dV. So for our case, we're always working with indistinguishable particles. So Q is equal to Q to the nth over n factorial. We can then make the substitution into the partial of Q by going up to this formula right here. And you see that this is what you get. So I'm going to use little q to the nth over n factorial, take the partial of it, and this is the result that we get. You see, we get a lot of cancellations. And we also remember that Q is the product of all of these partition functions. And the only one of these that is dependent on the volume, as we have seen, is the translational part. So QV, QR, Q electronic, those are all constants. We pull them out in front. And so this comes out to be dQt over dV. Here, I hope you appreciate the fact that I like to define the translational part as tau times volume. We don't have to stick that silly lambda to the 3/2 into the denominator. We'll take the derivative here with respect to volume, and you see it simply comes out to be tau. So amazingly, 1 over Q dQ dV comes out to be just 1 over V when we do it. We go back to the pressure formula we had up above. We still have our NKTs and little q's. Make this substitution right here for 1 over Q dQ dV, and this is what we get. And as I've been telling you the last few lectures, capital NK is little nr, and you'll notice this is the ideal gas law. P PV is equal to nRT. So statistical mechanics says that if you have an ideal gas, and I think all of you know about van der Waals gases and things like that, so you'd start getting some failure. But if you assume an ideal gas, you can go back and get the ideal gas law. Keep in mind that when we did this, the translational partition function went back to the particle in a box problem. So if you want to stretch the story a little bit, you can say the ideal gas law comes from the particle in a box quantum mechanical problem. Okay, well, I always thought this was pretty neat, even though I never saw this as an undergraduate myself. Okay, well, something else we might want is enthalpy. Enthalpy is internal energy plus pressure volume. We've taken out H0 and U0 here for the formula. Or, well, actually, we're sticking them back in, I guess, to be able to write it this way. And notice from what we had up above, we have a formula for pressure in terms of the partial derivative of the log of capital Q. And so we can write this whole business out again. This first term, again, it's U minus U naught. But the bottom line is that we have a formula for calculating the enthalpy. And you can ask your friendly computer to do it once you have put in the quantum states for translations, rotations, vibrations, and put in your temperature, you can get that calculation. The Gibbs free energy function is given by this. I learned it simply with the symbol F for free energy. And the way we were all taught to remember the formula, when this is F is equal to H minus TS, fish is horrible without tartar sauce. So I forget what those things are called when you have nice little slogans to help you remember formulas. But anyway, our Gibbs is horrible without the temperature entropy term that we have. So we can plug all of these things in here, again, come up with a formula for in terms of Q. Oh, okay. That's the word I was forgetting. Thank you. It's called mnemonics, I guess, spelled starting like pneumonia, PM. So English is a funny language, how P's and N's become different sounds. Okay. Anyway, I don't want to say anything much more about that. You can write these formulas for ideal gases. So G minus G naught winds up, you can see simply as the number of moles times the ideal gas constant times temperature times the natural log of little q over n. So quite possibly in your thermal courses, you've had to calculate G minus G naught. Now you can see if you could have figured out what the little q was and the number of molecules, that was another way to get this. But the very important thing I'm trying to impress by all these formulas is all important relationships come from the molecular partition function. The molecular partition function, as we've seen, it's strange. When I was taught this stuff, I was just told, here it is, this is what you do with it. I hope the fact that you've seen how Boltzmann derived it gives you a little bit of basis of understanding why the partition function can be useful. All right, well, we've basically run out of time. I think next time we'll probably be able to show everything else we want before we start doing what I call the super problem. And after we do the super problem, there's another practice problem. And on Monday, we will also go over a review that I will be sending out to everybody as such. So a lot of mathematical formulas here. I've tried to emphasize what's important by putting things into rectangular boxes like this one. Whenever we get to the exam, if you want to make life easier for yourself, well, actually, I'll make life easier for you when I send you the review sheet. You'll have a lot of these formulas on there, and so you can just utilize them when you need them for the examination. Okay, well, have a good rest of the week. We're roaring to the end of the semester, so keep your head above water if you can.